In this video, we are going to talk about how to solve systems of linear equations using the elimination method, which sometimes is called the addition method. So you may see it called either one of those too. And this time our goal is to try to get our two equations rewritten in such a way that we have opposite coefficients in one of the variables. So what I mean by that is, for example, take a look at this first example. You will notice that we have a plus 1y down here in the second equation and a negative 1y in the top equation. So those two equations have opposite coefficients in the y variable. That's the goal of the elimination method, that we want to get those two coefficients to be opposites. In this problem, we lucked out because our equations started out that way. So we're going to be able to go straight into the next step of the elimination method, which is that we're going to add the two equations. So you're going to add the equations. So let me rewrite them here. And again, we looked for these to be opposites, opposite coefficients. And now we add them. We get 2x. And see, because these two coefficients are opposites, when we add those two y terms together, they're going to give us 0y. The y's go away. So we have 2x equals 28. And now we get to divide by 2. And so now all of a sudden we have our x-coordinate right off the bat. Okay, now we need to solve for the y-coordinate, and to solve for the y-coordinate we'll go back to the original equations and we pick one of them to substitute x into and solve for y. So I'm going to pick the second equation, and the reason that I picked the second equation is because that's the one that has the y coefficient positive. Doesn't matter which equation you pick of the original two, it's a personal choice, and so I picked the second one. And now I substituted in my 14 for x, and now I'm going to solve for y. So y equals negative 2. So what we found is that the point of intersection is 14, negative 2. That's the solution. Now I always like to check my answers. Notice how I use the second equation to solve for y. That means I'm going to check in the first equation, the one I didn't use to solve for y. That means x 14 minus y minus negative 2, does that equal 16? And 14 plus 2 is 16. So that does check. Okay, so I checked it using that first equation. And so since we have one point of intersection, that means that we have a consistent independent system. Two lines that cross at one point. They intersect at one point. Okay, in our second system of equations, I immediately check, do I have opposite coefficients in one of the variables? This time I do not, right? But I do notice that I have a negative 5y here. And if I could just get that bottom y, this one, to be a positive 5y, then I would have opposite coefficients, wouldn't I? So guess what? I'm going to do that. And how I'm going to do that is I'm going to multiply the second equation by a positive 5. I'm going to rewrite the first equation. That one is unchanged. 6x minus 5y equals negative 1. And then I'm going to multiply the second equation by 5. And that has to happen both sides of the equation. This 5 gets distributed 3 times. Okay, so rewrite the first equation. Just going to keep rewriting because I haven't changed that. But the second equation becomes 10x plus 5y equals 65, because I multiplied that 5 throughout, right? And now look, now this is good because I have a negative 5y and a positive 5y. So I have opposite coefficients in the same variable, which means that I can now add the equations. And so I get 16x, this is 0, and then here I get 64. And dividing by 16, I get x equals 4. Now I get to pick, and I am going to pick the second equation to solve for y. So that's 2 times 4 plus y equals 13. So remember, I went back to the original equation and I picked one of the two, and the second one is easier, I think. So I put my x in and I get 8 plus y equals 13, which means y equals 5. But to check it, I'm going to check it now in the other equation, the first equation. So my check is 6 times 4 minus 5 times 5. Does that equal -1? Well, I have 24 minus 25, and that does equal -1. That checks. So what's our solution? Our solution is the 0.45. That's the solution to the system. And this is our consistent independent system, where two lines intersect at one point. Okay, so here in equation number 3, I want you to try this. I want you to go ahead, pause the video, try it using number 2 as a guide, and then come back and check my answer and see how far you got. Okay, so did you eliminate the variable y? That's what I did. And because it was easy to take the second equation and multiply by 2, did you do that? And so then, did you get 12x minus 2y equals 16 here in purple? And then we went ahead and added the two equations, and you got 16x equals 20, which is a reduced fraction of 5/4. Don't let that disturb you. And actually, but I used the fact that my x had a 4 in the denominator and chose the top equation to solve for y. See what I did? Because then the 4's would cancel. See, I was clever there. And so then I got 5 plus 2y equals 4. Subtracted, I got y equals -1/2. And then here's my check into the second equation. And so 5/4 -1/2 is the solution. And this is our consistent independent system again. So how did you do? All right, so we're going to go to the next problem now, which is a little bit different than the first 3. See if you can notice what is the difference in this fourth problem. This time around, in the first 3 problems, we would always have like a single y, right? Where it was easy to take one equation and multiply to make the coefficients be the opposites, right? But this time, we don't have that. However, we do have 2 coefficients that are opposites already in terms of sign. So they're opposite signs. So we have a positive 5y and a negative 3y. So at least the signs are right. Problem being that the coefficients, they need to be the same number. So now I want you to go back to your work with fractions. I know. We're going to try to do like a least common denominator here, or it's called the least common multiple. And that is, what's a number that both 5 and 3 will divide evenly into? Pick a small number, and if you said 15, then that's right. This time around, we are going to change the coefficients to positive 15y and a negative 15y, which means we're going to have to multiply both equations. So this equation, we will need to multiply by a 5, and the top equation, we're going to need to multiply by 3. And that's so that we can get exact opposite coefficients in those two y's. So I'm going to write it here. So I've got, here's my original equation. There they both are. The top's going to be multiplied by 3, and we're going to distribute. The second equation is going to be multiplied by 5, and we're going to distribute. And I'm going to rewrite them here on the side. So I get 12x plus 15y equals -6. And here I get 25x minus 15y equals 80. And so this was the whole purpose, that these two be exact opposites, which they are. Okay, so now we're going to go ahead and add them like we did before. See the whole purpose there? Okay, so here we now get 37x, and then here we get 74. And now we're going to divide by 37, so x equals 2. Okay, that's cool. And now we get to pick for the second variable, right? Which equation would you like to substitute x into? I'll go for the top one just because y is positive. So 4 times 2, I'm going to replace the x with a 2, plus 5y equals -2. So we get 8 plus 5y equals -2. And then we're going to subtract 8. And so we get 5y equals -10, y equals -2. All right, and does that check? Well, here, let's put the check up here, because we're getting that 2, -2 is the solution. So we'll check it in the second equation. So 5 times 2 minus 3 times negative 2. Do we get 16? 10 plus 6. Yep, that's 16. Okay, so that checks. So we once again have one point of intersection, which means that we have a consistent independent system. And the solution is 2, negative 2. In this next problem, we get to choose. We get to choose if we want to eliminate the x variables or if we want to eliminate the y variables. And looking at the way that the problem is set up, there is no one easier than the other. Do you agree? There's no opposites signs already, and there's no variable that has a coefficient of 1 that would make it easy. So it really is up to us. I think this time let's go ahead and eliminate the x variables. I'm not sure that we've done that yet, have we? So what number can we divide both 2 and 3 into? And if you say 6, that's right. So we're going to change one of the equations, one of the coefficients to have a positive 6x and the other one to have a negative 6x term. Okay, and we get to choose which one. So it's pretty random. I mean, it's a personal choice. All right, so here's our system. And so I'm going to go ahead and leave this one be positive 6x, which means that I'm going to make this next one be a negative 6x. So I'm going to multiply the top equation by a positive 2, the bottom equation by a negative 3. We distribute everywhere, right? Including that right-hand side. Don't forget that. Sometimes my students forget that right-hand side. So be very careful. And so now we add here. We get that 0x. We've eliminated the x's. And now we get here 1y. Oh, that's nice. Equals 3. So y equals 3. Now let's use the top equation. That works. 3x plus 8 times 3 equals negative 3. So we get 3x plus 24 equals negative 3. Subtract 24. So we get 3x equals negative 27 and divide by 3 and x equals negative 9. Does it check? Let's check it in the bottom equation. So we have negative 18 plus 15 and that does equal negative 3. So our solution checks. And what is the solution? The order pair negative 9, 3. We're back to the same thing where we have a consistent independent system, right? Okay, how'd you do with that one? Is it making sense? Okay, so here's our last problem. I'm going to say, let's eliminate the x's again. And I'm going to say that we can get that numerator to be a negative 20x. So we're going to multiply by negative 5. Okay, so I'm going to write this down here. We're multiplying times negative 5, and we have to multiply all across here. Now, this bottom equation is going to stay the same. So I'm just going to rewrite that because we did not alter that in any way. But over here I get negative 20x minus 15y equals negative 10. And when I add those two, what do you notice? I get 0 equals 0. My variable has canceled away. My variable is 0x and 0y. All variables have canceled away. And I'm left with a statement. Is it true or false? It's a true statement. So this is one of our two special cases. Which one is it? If you said this is the one where we have an infinite number of solutions, you're right. These are the same line. Infinite number of solutions. The graphs have two lines that are the same. So all the order pairs in the line are solutions to the system. And so that is called our consistent dependent system. And there's an infinite number of solutions.